So up above here I have the harmonic series 1 over n, which we saw diverges. That's just a p-series where p is 1. And the screenshots here of my calculator are just meant to show you how slowly it does diverge, which is a strange thing to say, but the point is if you add up the first 20 terms, you get 3.6. Even if you add up the first 500 terms, you're still only at 6.8, and yet this goes to infinity eventually. In other words, this sum is not bounded. There's no limit to this sum. So that just gives you a sense of how slowly that diverges. That just barely misses the cutoff for a convergent series. In general, the p-series we've looked at, they're common choices to use as comparisons when we use what's called the limit comparison test. So the way the limit comparison test works, and again it works similar to what we did when we did improper integrals, is that let's say you've got a series you're interested in analyzing. You've got another series whose behavior you know, so you know whether it converges or diverges. If you just look at the limit of the sequences, and that goes to a number that's in between 0 and infinity, then they behave the same way. They either both converge or both diverge. And p-series are going to be very useful in these type of tests because we know what all the p-series do, right? We know the rule for p, the condition on p that makes the series converge or diverge. So those are very useful, as we'll see in the next few examples, as series to compare with ones that we are trying to analyze. So the limit comparison test is useful in situations like these. So let's look at this first series, 5n over n squared plus 4. So what I want to point out is that, so I'm going to circle that. This behaves like and again, I'm not talking about the series, the sequence. That behaves like, well, in the long run, that plus 4 is not so critical. So it behaves like 5n over n squared, which is just 5 over n. For large n values, they're very, very close. So couple that with the fact that we know that series diverges. And we know it diverges because it's just a p-series where n is 1. That 5's not important. You could factor it out and put it in front of the summation symbol. And you just have 5 times the divergent series. So this clearly diverges. So to show that, that basically tells us that the one that we're analyzing diverges too, but the limit comparison test is what makes that clear. If we take the limit as n goes to infinity of 5n over n squared plus 4 divided by 5 over n. Okay, so I'm taking the limit of the sequences that are associated with these series. Well, that equals after a little simplification, that's just 5n squared over n squared plus 4. But that clearly equals 5. And since that is, since 5 is not infinity and it's not 0, that implies that that series diverges. So that's the limit comparison test. Ultimately, you sort of know, just at a glance, you know what it's going to do or not, and the actual comparison test that I'm showing is just proof of it. But your choice of the series here, or the sequence inside the series to compare it to, your choice of that really indicates that you know ahead of time what it's going to do, right? If you're choosing 5 over, to compare it to 5 over n, you probably did so because you knew that this series 5 over n diverges. So everything else here is just showing your work and supporting that idea, supporting that conclusion using the limit comparison test. So let's try another one. This series here, I would say that this sequence behaves like, so that plus 1 is not that important. It's going to behave like 6 over 3 times 5 to the n for large n values. So that means, and so why we choose that? Well, this is 6 over 3 6 over 3 with 5 to the n in the bottom. That's just the same as, so 6 over 3 is 2, I can take that out. 1 to infinity of 1 over 5 to the n. But that's just 2 times 1/5 to the n. And that's clearly a geometric, which we know converges. Right? It's geometric. And now what we just need to do is use the limit comparison test to show that clearly these are, that the ratio of the sequences goes to a number, a non-zero number. So I'm going to take the limits, zoom in here. So if we take the limit as n goes to infinity of our original, and divide it by the one we're comparing it to, so 6 over 3 times 5 to the n, let's just express that as 2 over 5 to the n. Multiplying by the reciprocal gives us 6 times 5 to the n divided by 6 times 5 to the n plus 2, if you distribute that 2 to the 1. And if it's not clear what this is doing, what you can do is you can divide all the terms by 5 to the n. So when you divide the top term by 5 to the n, you get a 6. You divide the bottom, the denominator, by 5 to the n, you get 6 plus 2 over 5 to the n. And so therefore, as n goes to infinity, this becomes 6 over 6, which is 1. And that allows us to conclude that this series here that we were analyzing to begin with behaves the same way as 6 over 3 times 5 to the n, which we know converges. So this converges too. All right, and again, so when you're, if you think about it, when you're taking the limit of these two sequences, you're interested in basically, in some sense, their growth over the long run, or their behavior over the long run. Anytime it goes to a real number, we're saying that they behave the same way in the long run, and so the infinite sum should behave the same way as well. Let's finish with this one here. This is 2n plus 1 over n plus 1 cubed. And I would note that I would just note that 2n plus 1 over n plus 1 cubed, if you imagine expanding the denominator, you're going to get an n cubed. And in the long run, as the highest power, and in the long run, that term is going to behave like, or that sequence is going to behave like 2 over n squared for large n. So I've sort of anticipated what I should choose, because again, we're not actually going to expand the bottom out, but I know it's going to be n cubed plus some stuff. And 2n, the plus 1's not that important. It's 2n over n cubed is 2 over n squared. And but we know what this does. That converges because it's a p-series with the 2 multiplied, which doesn't affect anything. So basically we know that's this example here, the letter C is going to converge 2. To actually prove it, we simply show the limit. So this ends up being, so multiplying by the reciprocal, you get 2n cubed plus n squared divided by 2 times n plus 1 cubed. And without doing that out, we can see that that clearly equals 1. So that implies that this converges too.